Hello. Let's see how to get from this representation of Fourier series to this one, more compressed, where an, bn, cn are coefficients of Fourier series. To develop this relation, I need to see earlier formulas. So we know that exponential of something is equal of exponential of jx is equal with cos of x plus j sine of x, and if I get exponential of minus jx, that will be cos of minus x plus j sine of minus x. But if we look at the sine and cos, we know that this is a cos of an angle and this is sine of an angle, while cos of theta is equal with cos of minus theta. And how about sinus? The sinus will be sinus of theta. It's equal to minus, sinus of minus theta is equal to minus sinus of theta. This is a minus sinus of theta, and minus sinus of theta. So that means my relation here will change into cos of x minus j sine of x, which means if I perform sum of these two relations, I will get exponential of jx plus exponential of jx. I'll get 2 cos of x, and I'll write here cos of x is equal with exponential of jx plus exponential of minus jx divided by 2. Same way, if I subtract exponential minus jx to exponential jx, I'll get j2 sinus of x. So sinus of x, it's equal to exponential jx minus exponential minus jx divided by j2. Now I'll develop this cos and this sin according to earlier formula. Well, I will get an exponential of jn omega t plus a minus j and omega t divided by 2 plus bn exponential of j and omega t minus a minus e minus j n omega t divided by 2j. Now I will regroup terms with e j n omega t. So that will be a n divided by 2 plus b n divided by 2j exponential of j n omega t plus a n divided by 2 minus b n j2 exponential of minus j n omega t. I know that if I have n divided by j, I can multiply by j divided by j and I'll get j divided by j square, which means we got minus j. So here we'll have minus jbn divided by 2. So here we have minus j, and here we'll get plus j. So are you right? Plus an plus jbn divided by 2. Exponential of j minus n omega t is the same thing, but what is important is I would like to get here minus n index. So how to do that? But to do that I need to know the relation of an and bn coefficients, and an is an integral of the function cos n omega t dt. So if I want to get minus n here, a minus n, the formula will change only here. So I will get cos of minus n omega t, but we know that cos of minus something is cos of something, which means that an is equal to a minus n. For bn, it's the same thing, it's the same logic. bn is an integral as well, but with a sinus. So if I replace the n by minus n, I will get sinus of minus something, which gives me minus sinus of something. And I can write that b minus n is equal to the same integral, but with the minus in front of the integral, which means bn is equal to minus b minus n. So now, taking into consideration both expressions, I will replace a and bn by the result which we have here. That will give me an minus jbn by 2 exponential of jn omega t plus an a minus n minus jb minus n divided by 2 exponential of j minus n omega t. We know that we can split a sum into a sum of terms. So I can split this sum in two sums. Omega t plus the second sum a minus n minus jb minus n divided by 2 aj minus n. And let's get, instead of minus n, let's get n. But we'll have to change the domain of this sum. Well, that will be an minus jan plus, and now we'll have minus to 0 because we changed minus n by n. So now we got a sum which get a larger domain. Going from infinite minus infinite to plus infinite. That's the difference between this sum, which goes from 0 to plus infinite. This one will go from minus infinite to plus infinite with a term of an minus jbn divided by 2 exponential of jn omega t. And our term cn is actually an minus jbn divided by 2 and this is how we done to prove that this formula with this one the same. It's just another representation of Fourier series. Thank you.